I'm going to talk about something called packet loss recovery in the video streaming scenario. So this is mainly a video streaming work, and it is related to the edge, so I guess it's in the edge session here. So I remember I was talking in the last talk, asking the question that why we are still working on crawlers in the recent 30 years. I'm more like a TCP person, so in my case it will be 40 years or even longer. But we are still working on that because we do see more and more different applications that requires extremely low latency here. For example, here I just downloaded several random video clips from the social medias showing, they are all generated by the graphics applications, by the way, they're not the real world. But they are all showing what the world is going to be if you have the AR, VR headsets or glasses. You can see that all of these things, like the road signs or the labels or all of the other indications, they are rendered by the computers in the remote places, and they are streamed. And the streams will be patched on what you are going to see through your glasses. So even if there's a single tiny latency fluctuation, that will make the alignment to be misaligned, which we can see some mismatches between the road signs or the people you can see in the scene. So that's why we want to have an ultra low or an ultra consistent low latency here. Because if you're going to vary these things for the whole day in the future, maybe 20, 30 years later from now, you will heavily rely on that. For example, if you think, I can see many of you are wearing glasses just as me here. If you wear the glasses, you take on the glasses, put on the glasses in the morning, you only take them off in the evening when you go to bed. It's 10 plus hours. If there's a single fluctuation, maybe it's only, let's say, 1 second or something, that happens in your glasses, and let's assume you are wearing AR glasses 20 years later, that might be fatal to your life because you might be heavily relying on that. So that's the thing. So imagine why you are wearing AR glasses now for 20 minutes, 30 minutes, and start to feeling dizzy. The reason is that the latency is still kind of fluctuating, and we want to focus on that. So to give you a more intuitive example on what is the latency fluctuation, here's another video we made on showing the latency fluctuation of 0.3 seconds. You can see just now, let me follow this video for a while, and you can see here exactly. That was a 0.3 second stop. You can see the racing car here has already made the turn. So if you use your AR glass just out of service for 0.3 seconds, the driver might be just rushed out of the road. And this requires extremely low and extremely tail percentiles that we want to optimize. So let's say you are considering a 0.3 second stop every 5 minutes. 5 minutes is not a long time, right? We are going to make sure it's going to behave well in the 10 hours. Even if it's 5 minutes, the ratio of 0.3 seconds over 300 seconds is 0.1%. Okay, so that's why our work is trying to reduce at this tail percentiles. So if you take it from the view of the latency at the tail percentiles, you can see that it is composed by two components, basically. One is, of course, RTT, right? How long does one packet take from the sender to the receiver? And the other part is how many times will this packet be retransmitted? Why is that? If you're considering from the median percentiles or the average numbers, you will not care about the retransmissions at all, right? Because in the large likelihood, the packet will not be discarded. But if you consider the position of the last 1% or last 0.1%, you have to consider the loss. So for a single packet, the time it takes from the sender to receiver is the RTT. And how many times it needs to take to be delivered from sender to receiver is the RTX. For example, one packet may be transmitted once, dropped. The second time dropped, third time dropped, finally delivered in the fourth time. Then the time will be 4 RTTs in total. RTT is mainly dominated by the congestion control or the link conditions and also the queuing delay, which is not the scope of this paper. And you can refer to many other papers to check on how they are going to optimize the RTT. Here we focus on the RTX, the loss recovery mechanism. So a very typical and common loss recovery mechanism is called FEC, forward error correction. What does it mean? So in the video streaming, especially those low latency video streaming, they are so afraid of retransmission. So they come up with a coding mechanism called FEC, which they will compose some redundant packets. For example, if you're going to send 3 data packets in blue here, no matter which one of them is lost, you have to retransmit, which is not good for the users. So they have a coding mechanism to generate the fourth packets here and form them into a block. They send this block to the receiver, and no matter which one out of these 4 packets are lost, the receiver can always recover the original 3 data packets to make sure the scenes or the contents is still the same as the user expect to be. There are plenty of work on that, like on designing different algorithms, on determining what, like here the ratio is 1 out of 3, right? You're going to apply a redundancy ratio of 1 over 3. But on how to optimize this ratio, on how to optimize a lot of different factors, there are many work on that. But here's the difference. Now the latency goes down. Imagine like 30 years ago, the latency or the RTT between 2 parties is like 100, 200 milliseconds. Then one single retransmission can be bad for the user experience. But then now the RTT is only 10 to 20 milliseconds. You can just, I know the Wi-Fi here is not very well if you are using your laptop now or like in the last 2 days. But the fact is that the general RTT in the internet nowadays is from 10 to 20 milliseconds because of many different mobile and Wi-Fi techniques developed recently. And this is not just the ping latency. Here's a measurement paper from IMC 2022. They measured 3 different cloud gaming platforms ranging from the Stadia to the Amazon and also the NVIDIA ones. They are testing with the 30 Mbps-ish rate. At that standard rate, the latency, the average latency is still 10 to 20 milliseconds with the standard deviation in the brackets. So that's quite good. So what does it change to the loss recovery? When the RTT is so low, it's to the level of 10 to 20 milliseconds, we humans cannot tell the difference of that low of RTT. When there are 2 packets, one frame is like 100 milliseconds, the other is 200 milliseconds, you might be immediately able to tell the difference, right? But when there's a packet that comes in 10 milliseconds, the other comes in 20 milliseconds, we human has kind of biological limits which prevents you from telling the difference from 10 to 20 milliseconds. There are a lot of like CHI papers on studying what is the limit, where the limit is. There might be different depending on different people, different applications, and different scenarios, and even different contents. But the general rule here is that it is bounded by like 50 to 200 milliseconds. So now this gives us a chance. This is where Hairpin lies in. We are going to optimize the space where some kind of retransmission is acceptable, but not many. So this gives us space to trade off between the redundancy and retransmission. So the question will be, when the network is lossy, are we going to add some redundancy? Or are we going to add more, like just wait for the retransmissions? So what we're going to do is that we're going to co-design them. So here's an illustration plot showing what is our design space. So there are a lot of related work that I just showed you in the FEC slide that they optimize the redundancy rate based on different network conditions like loss rate, RTT, and so on. And there are also other lines of work which try to detect the packet loss immediately, which is on the vertical line. We are going to do the joint optimization here. And that's it. That's the simple idea here. So the simple takeaway from Hairpin is that when there are many chances to transmit, just do not use the redundancy code because that's a waste of bandwidth. And that's also not good for like the CPU overhead and so on. So just rely on the retransmission. But when the time is running out, the deadline is approaching, we can aggressively apply more and more redundancy to the packet so that it is still able to deliver the packets before the deadline. So putting it in the plot ways that like many legacy methods, if they're not aware of the remaining time budget for the packets, they will, no matter what the remaining time is, use the same redundancy rate based on network conditions. But we are going to make it adaptive to different scenarios. So let me show you an example here on how this works. Suppose the loss rate here is 20% and RTT is 20 milliseconds, and the deadline, which is the application requirement, let's say here 50 milliseconds. That means you can transmit one and also retransmit another time, but not retransmit for the second time, right? You can deliver 2 times. So in the legacy method, they know the loss rate is 20%, so they might apply a redundancy rate of another 20%. So let's assume we're going to deliver 10 packets here. So they add another 2 redundant packets. Since the loss rate is 20%, that means the loss can be fully recovered, right? So they do not need to need to try a second round of retransmission. That's it. That's out-delivered. They can out-deliver the packets in the first round. And Hairpin, because in the first round it is still far away from deadline, we do not apply any redundancy. So that means the redundancy rate is 0%. That's not good because we will have 2 more packet losses. So we will have go through another round of retransmission. So in the second round, let's say we apply a redundancy rate of 50%, and it can of course be recovered because the loss rate is only 20%. Sounds like we are be heavily beaten by the legacy method, right? But the thing here is that if you say the loss rate is 20%, is it really 20%? Because our project starts on trying to predict what it is loss rate. And loss itself is a very small probability event in the internet, right? It happens only in the very rare cases. So if you're going to try to predict a small probability event, it's going to be very inaccurate. We try different models, we try Markov chains, we try Gilbert models, like so many models, and they're not working very well on the internet. So let's say you thought the loss rate is 20%, but it turns out to be 40% when you are trying to send more packets. How will different methods behave here? In the legacy method, they have no idea about this, so they still send 2 more redundant packets, and 4 of them are lost. They send another 20% of redundancy, which is 1. Another 2 will lost. And we just use the rounded up, so we can add another redundant packet in the third one. Finally, it can be delivered to the client side. But in this case, it has already taken 3 times of the RTT, so 60 milliseconds. It is already break the deadline, which is not good. But in our case, since we are leaving more redundancy room for the follow-up packets, we will be able to have more recoverability with higher loss rates. So what's the benefit in general? Benefit 1, we can have fewer deadline miss rates because we are going to have much higher protection rate or the redundancy rate for the retransmission packets, which is good for the case of the uncertain loss rate scenarios. But another benefit is also the bandwidth, right? Maybe you have never thought about this before, but protecting all the packets with only 10% of the redundancy rate is the same bandwidth cost as protecting only 10% of packets, but with 100% of the redundancy rate. They are the same on bandwidth cost, but they are totally different on the recoverability, right? Because we are only focusing on those lost and retransmitted packets, the traffic volume is much fewer than the other original data volume. So we can also save bandwidth if you count number of packets here. The left hand is 20 packets in total. It is 12 in the first line and 5 in the second line, 3 in the third line, so 20 in total in the left side. But with Hairpin, you can only get 16 packets. That's why we call it Hairpin. If you're a good player at badminton, you can see that usually badminton players will try to play the shuttle back as high as possible because you're going to control over the other court. But what Hairpin do, or here is called Hairpin shot. What Hairpin shot is going to do is that it just intentionally wait for a little bit. Unless the shuttle is not reach the ground, that is the deadline for a shuttle, right? Unless shuttle is not reach the ground, you still have the space to play it back, and sometimes you can have better performance. Sure, there are a lot of design challenges behind this, like there are some temporal dependency. For example, the redundancy rate you are going to set will affect how many packets is going to be lost and recovered in the next round, right? There are temporal dependency. And there are also spatial dependency, which is very related to the FEC block size. If you remember in the beginning of this talk, I talked about the blocks of FEC. It's also changing the results. And also a lot of other challenges. And we actually have a Markov chain on it. But to be honest, the majority of the performance benefit is coming from the idea of differentiating retransmission from the initial transmission. The further optimization is only contributed to maybe the 1/4 of the whole performance improvements. We finally have evaluation on that. We have an NS3 simulation here based on another simulator we had in the CCOM 2022 on Zhuge. We have different sets of bandwidth traces. We have different baselines. And the metric here is to trade off between the deadline miss rate and the bandwidth cost I just showed you. Between all the baselines, we run the GCC congestion control algorithm here in the simulator. We can see that our method is basically trying to push the Pareto optimal frontiers of all the WebRTC and academia papers front by a little bit. I can see, as you can see in the red star in this figure. Okay, since time is running up, I'm going to show another slide on how to understand the results here. This is more important. So bridging back to the starting point of this talk, we are going to differentiate different retransmission or transmission runs. So what does this plot tell us? You can see from these three plots here, the L1, L2, L3 determines how many runs of retransmission it is still left. For example, the RTT is 20 milliseconds, and the time to the deadline is, let's say, 50 milliseconds. Then you will have 2 runs of transmission. That is L here. So with the darker the color is, that means the more redundancy rate Hairpin is going to apply. So you can see with the much fewer transmission chances or runs, we will have a much more aggressive redundancy rate, which can be up to 500%, which is 5x, right? Just duplicate to 5 times. That still saves bandwidth because it's only a small portion out of data volume. We have more evaluations on different congestion algorithms, like different metrics and different parameter sensitivities and so on. Please just go to the paper for more details, or I will just stay here to chat with you if you have more questions. Okay, so the simple takeaway for this talk is that when thinking about a packet loss recovery, it is not only about duplicative ACK, not only about timeout, not only about the redundancy rate. You need to think all the things together to make sure the packet can be recovered in a timely and economic way to save bandwidth and reach the deadline as most as possible. And we have open source our NSDI simulator, and we also recently, this is not in the paper by the way, we also recently implemented in WebRTC with the M119 branch. If you are interested in deploying this WebRTC, you can also try our new patch on it. All right, thank you for coming to my talk, and I'd like to take any questions.